Good morning, everyone. My name is Stacey Alberts. I'm research faculty at the University of Arizona and a member of the US MIRI GTO team. So I want to start by thanking the organizers for inviting me to lead off this galaxy evolution session. It's really been an amazing 2 days of just seeing all of the stuff that JWST has been doing in its first year and a half and discussing the broader implications of that. And I also want to thank Marcia for letting me borrow her super awesome JWST jacket for this occasion. So on Tuesday, we heard from Sandro that one of the primary drivers of JWST's mission is, of course, to peer back into the early universe and try to understand the emergence of the first galaxies and black holes, and really characterize the first billion years of cosmic history. So the capabilities that allow JWST to do this, also to really push that frontier, also allow us to have a much more intricate view of the physics of how galaxies evolve at what we're now jokingly calling low redshift, otherwise known as pretty much the rest of cosmic time. So understanding galaxy evolution has been a monumental effort ever since we first realized that galaxies are actually external structures to our own Milky Way. We now know that galaxies evolve through a combination of processes, both long time scale processes like gas accretion from the cosmic Webb, and more discrete events such as galaxy mergers that may trigger a massive starburst and the feeding of a black hole. The relevant prevalence and details of the different evolutionary scenarios that we've come up with so far are still kind of, an open question. So take, for example, here what I'm showing. So this is kind of a long-standing evolutionary sequence for how we think maybe very, very massive galaxies evolve. So we start with kind of a disk galaxy, but then maybe the disk galaxy has a neighbor, and we have an interaction which triggers a chain of events. Gas is funneled into the core of the coalescing galaxies, which drives a period of vigorous star formation and feeding of the black hole. So this can cause the development of a reddened embedded quasar, which will eventually build up to a point where its feedback is strong enough to have a blowout phase, which removes whatever gas and dust is left in the galaxy. So post this blowout phase, we might see an unobscured quasar, and then eventually we would expect this to become a massive red and dead elliptical. So this picture was developed via our observations of massive bright galaxies that are relatively nearby for the most part. In other words, this is kind of the easy case, observationally speaking. And yet, confirmation of this pathway has eluded us. For example, the dusty nature of the coalescent phase has made it very challenging to confirm whether some of the nearby very massive galaxies actually do have active black holes in them at all, much less kind of a developing very bright quasar. So such is the case in the corner up here of ARP 220. So these are JWST observations of ARP 220. So we're actually looking at this with the MIRI IFU as part of one of our GTO programs, and so stay tuned to see if we can solve this mystery. But that's kind of the case for very, very massive galaxies. What about more normal galaxies or isolated galaxies? So we've long observed that there is a bimodality up here on the left in the colors, the galaxy colors and shape. So massive galaxies are usually either blue and star forming or red and passively evolving. And so they're kind of thought to move from this blue cloud to the red sequence. So how does that movement happen? From observations in theory, most massive galaxies grow via kind of an extended period of sustained star formation fed by new gas accretion from the cosmic Webb. And it's regulated by internal processes that both consume and eject gas. So this is kind of the bathtub model that Sandro brought up on Tuesday. So this regulation is thought to give rise to what we see here on the right, which is the main sequence of galaxies, where most galaxies are forming stars at a rate that correlates with the existing amount of mass. Unusual rates like those in starbursts, where star formation is very efficient, are thought to occur via more discrete events, such as the major mergers we talked about in the first example. So sustained star formation can be maintained on long timescales by the cosmic Webb, very long timescales. However, we know from the abundance of galaxies that have stopped forming stars at all epochs that we have to have something that intervenes and forms the red sequence more prematurely. So commonly invoked in massive galaxies is AGN feedback. However, observing this process has also been challenging due to the complexity of galactic ecosystems and the multi-phase ISM. And we don't need to just, we need to also, in addition to explaining the halting of star formation in galaxies, we need to explain why they have a change in their shapes. And the origin of this structural change has been challenging to establish. Are mergers or interactions necessary? The lack of access to rest frame near infrared prior to JWST, especially at high redshift, has made it difficult to measure the merger rate due to things like cosmic dust and needing to detect a faint stellar surface brightness. And of course, these evolutionary pathways are going to change with cosmic time. So we saw this in Sandra's talk Tuesday. This is the star formation rate density of the universe, which has been split into its infrared and UV components. And you can see that it rises steeply through cosmic dawn. It peaks at cosmic noon, where there's an abundance of gas available and favorable black or dark matter halo masses. And then we see this decline towards present day. And so, with HST, we were able to really sensitively and with high resolution probe the rest frame optical at cosmic noon, and then the rest frame UV at cosmic dawn. Of course, the UV is only tracing really the youngest star formation, and it's really kind of a small component of what's going on. So now with JWST, we can probe the rest frame near IR and mid-IR up to cosmic noon, near IR beyond cosmic noon, and then optical all the way back into the early universe. So if we put this all together, we can come up with some overworked questions perfect for JWST. So how do galaxies get their shapes? How do galactic ecosystems change over cosmic time, and how does this affect their ability to form stars? What is the role of black holes in shaping their host galaxies? And then finally, why do galaxies stop forming stars? So to address these questions, the field has made a monumental effort to design both targeted observations and then many large surveys of both local galaxies and our favorite extragalactic fields. Many of these surveys take advantage of JWST's parallel capabilities to have both an imaging and spectroscopic component, so they're very powerful. So what can we do with all this stuff? So let's start with talking about galaxy shapes. We're going to hear about this in more detail later from Jehan's talk, so I'll have a little brief introduction. So the high spatial resolution in the rest frame optical with JWST up to cosmic noon allowed us to trace the Hubble sequence of galaxies. So this is kind of classifying galaxies as spheroids, disks, and kind of irregular galaxies. So now we want to trace this back to cosmic time. So as you can see here, going from left to right, it quickly became apparent that galaxies in the early universe were intrinsically redder, seen here up to about 11 billion years ago. But we saw many of the same shapes that we see today, indicating that the Hubble sequence actually originated much earlier. So we want to know when the formation of bulges and stable disks and spiral substructures begins, and that can tell us a lot about the processes that assemble galaxies at early times. But we didn't just see orderly disks and spheroids with HST. We also saw a rise in the fraction of kind of regular galaxies with clumpy substructures, which is what you're seeing here. However, again, with redshifting, when we got above redshift 2.5 or so, HST started to probe just the rest frame UV, tracing only the youngest, most recent star formation, and so this can give you a biased view of the overall galaxy structure. So in addition to changes in morphology observed with HST over time, it was found that a galaxy's size and its stellar mass were correlated. This relationship was found to also strongly evolve with redshift. But even where HST was able to see the rest frame optical light and suffered from biases, we could have optical photons being absorbed by cosmic dust. And near the peak of star formation in the universe happens to be a very dusty place. So if this dust is distributed differently than the stars, say if it's more compact, this can result in an overestimate of the measured optical size. So this was quickly shown with JWST, which is being shown down in the bottom right, with NIRCam, which is diffraction limited up to 4 microns. And this allowed us to measure the rest frame near-infrared sizes, which are more robust against dust extinction. And so it turns out that massive galaxies, which are very dusty, were having their sizes generally overestimated by factors of 1.5 to 2 in this particular study. And this means we need to rethink the evolution of the mass-size relation with redshift and the implication for how galaxy growth is occurring. So what does JWST see in terms of morphologies? On the left here, we see HST, and we could, if we were looking at these galaxies, we might classify them as clumpy irregular galaxies, or we might not see much of anything at all, which is the case with the middle example. And then when you get the JWST data, these grand design, spiral designs, these central bulges, and these disks are revealed. So initial results with JWST are broadly kind of showing that the Hubble sequence is apparent up to redshifts of as early as 6 or about 1 billion years after the Big Bang. and we need to look even earlier for its origins. Or at least that's the case for massive galaxies. JWST's sensitivity to redder photons is allowing us to extend the range of our studies down to lower masses, and here we recover a kind of regular morphologies that rise with, the fraction rises with redshift. So JWST is significantly altering the way we think about galaxy shapes, but we might have a long way to go to make full use of its capabilities. I'm showing just a few examples of some interesting stuff that we've seen so far. So on the left, we see a combination of a JWST and ALMA submillimeter imaging, which discovered a large gas-rich off-center substructure in what was apparently kind of a normal disk galaxy at redshift 3. In the middle, we see color gradients that reveal star-forming regions, red star-forming regions, surrounded by more extended blue quiescent regions within galaxies, sometimes symmetrical and sometimes lopsided, which might indicate external disturbance. And on the right, if we subtract out bright elliptical galaxies in near-cam imaging, it's been revealed that there's an abundance of companions and a mass ratio of 1,000 to 1, which is 100 times better than HST was able to achieve. And these companions kind of support this theory that minor mergers are important in driving the structural evolution of quenched galaxies. So closely related to morphologies of galaxies is the physical and chemical processes going on in the interstellar medium. Now we're kind of changing topics, and we want to talk about the inner workings of galaxies on smaller scales. So fundamentally, galaxies are responsible for processing the baryons that make up pretty much everything familiar in the universe. The baryon life cycle is responsible for forming elements heavier than hydrogen and helium created in the Big Bang. And JWST, particularly with its amazing spectroscopic capabilities, is opening kind of an entirely new window on stars and star clusters and the exchange of energy in the ISM. So in considering this section and the literature and all of the possibilities in this topic, there was basically an overwhelming amount. So instead of trying to be comprehensive, I'm just going to go through some quick examples of investigations cycle 1 from the local early universe that are kind of showing the range of what things we can do. So starting in the local universe, and this is going to be what we're going to hear about this more in Janice's talk, we're enjoying unprecedented spatial resolution in the infrared, which can isolate star-forming regions, capturing young stars that are cocooned in their dusty birth clouds. So with MIRI, which is what we're seeing here, you can look directly at obscured star formation relative to dust geometry and understand dust attenuation at shorter wavelengths. On the right, you can see the mapping of bubbles and voids in the ISM, and this is outlined by orange regions that are showing H-alpha emission from HST, which is giving us a detailed view of the process of stellar feedback with JWST imaging. More expensive, but of course extremely powerful, JWST spectroscopy can access near and mid-infrared spectral features that contain a wealth of information. So on the top right, we see the distribution of low ionization emission lines in central regions of a Goals galaxy, compared to more centrally concentrated high ionization line emission and shocked molecular hydrogen lines. This is tracing a black hole. On the lower left, we see more high ionization emission lines that are tracing black holes in this exquisite MRS spectroscopy. And on the bottom right, we're seeing dust features in the mid-infrared, so we can really start to trace what the small grain dust in galaxies is doing and how it interacts with the physics and the chemistry of other components in the ISM. Now moving to the peak of star formation activity at cosmic noon, JWST's resolution in imaging can again resolve the distribution of stars in very dusty galaxies, robust against dust extinction. And for the first time, we're able to see things like bars, measure the bar fraction in early galaxies, quantify their role in funneling gas into galaxy centers, which is something we think is important in the local universe. And then on the right here, we see a study by JWST MIRI, which can spatially resolve obscured star formation through dust features at cosmic noon and see how the compactness of dust relates to how you're forming stars. Okay. And then as we move up to cosmic noon and beyond, we gain access to the workhorse strong optical emission line features that we know so well from JWST, as well as a whole new suite of diagnostics for conditions in the ISM. For the first time, we have access to Passion alpha and bracket lines, which are a gold standard for measuring instantaneous star formation rates. As we saw with much excitement with the first release of the JWST images, we can now detect auroral oxygen lines that are direct tracers of the amount of metals in a galaxy. We can access things like shock diagnostics, neutral and ionizing gas tracers, trace the multi-phase ISM, including outflows. And then on the left, that's what we're seeing here. We're seeing a stellar absorption feature where its shift is indicating a large-scale neutral outflow, which contains significantly more ejected mass than the ionizing outflows that are kind of more commonly observed, because it's easier to look at the ionizing lines. So linking the molecular, neutral, and ionized outflows in galaxies at cosmic noon is really going to be key to understanding the effects of feedback. Okay, and then last but not certainly least, JWST can now measure star formation histories and ISM conditions up into the first billion years of the universe. So I'm not going to talk about this too much because we're going to hear details in the talks coming up by Anna and Karina. So I'll just say that having access to UV and optical emission lines combined with imaging is a very powerful probe of things, and we're revealing bursty stochastic star formation histories, complex gas kinematics and outflows, and extreme ISM conditions, both in galaxies and kind of around their black holes compared to the local universe. All right, so now we're going to turn to, how much time? We're going to turn to talking a little bit about black holes and how they influence their host galaxies. So at first glance, it's not actually obvious that black holes should have a lot of effect on their galaxy's evolution. The scale of black holes, their accretion disk from Taurus, kind of measured on the scale of maybe tens of parsecs, while its host galaxy can extend over several kiloparsecs. So nevertheless, we have compelling reasons to believe that black holes play a large role in galaxy evolution. On the left here, we see the Megorian relation, which is a tight relation between black hole mass and galaxy mass, or alternatively, the galaxy velocity dispersion. In the middle, we see again this peak in the star formation activity of the universe, peaks at cosmic noon, and now we see that it also, there's a peak in the black hole accretion rate around the same time, which is suggesting a link. And then, as mentioned in the intro, AGN, or quasar feedback, is often invoked to stop massive galaxies from forming stars in simulations. So prior to JWST, understanding the details of the relationship between black holes and their galaxies was kind of limited, especially as we went into the early universe. Above redshift 4 or so, we could only identify the most luminous quasars, so luminous that their light vastly outshined their host galaxies. And between this and HST's limitations to observing UV light at these redshifts made the host galaxies very challenging to understand or detect at all. JWST's access to optical, where the ratio of quasar to host light is more favorable, gives us a fighting chance. So this is demonstrated here in a study of 5 redshift 6 quasars we observed with NIRCams. This study, 2 papers have been put out now by a student in our group. So the quasar is, of course, a point source in a more extended host. So a properly scaled PSF can be subtracted from the quasar image to search for the host galaxy below. So according to the Megorian relation, their host galaxies should have been, relatively detectable. Instead, we found very faint extended galaxy emission, or really only upper limits in a lot of these cases, which places these quasars well above the Megorian relation, which is the stars in the plot on the right. So this is kind of answering a cosmic chicken and the egg conundrum. JWST was revealing that black holes grow kind of first and rapidly, leaving their host galaxies to kind of catch up later, so that we establish the Megorian relation in the later universe. And we saw this in Sandro's talk on Tuesday a little bit. It's not just luminous quasars. JWST is now giving us access to more moderate intermediate mass black holes at high redshifts, and Roberto has shown that this is they're showing this similar behavior. So another example of the potential new population of modest black holes by JWST is the peculiar case of the so-called little red dots. The little red dots are very compact galaxies that have an upturn in both the UV and the infrared, giving them a characteristic V-shaped spectrum. These galaxies have been modeled as a stellar spectrum plus an AGN component, and you can kind of see a schematic here on the right where our line of sight is catching kind of the red and black hole, giving rise to this power law in the infrared, and then we have scattered blue light that's causing the UV upturn. Okay. And indeed, when we follow these up with spectroscopy, we find that several little red dots do have this broad line component that is showing that they do, in fact, have black hole. Some of them also turned out to be brown dwarfs. So we want to know if this bromide component is coming from the scattered light, like in the schematic, or if it's more direct measurement, and is the red and black hole emission causing this rise in the IR spectrum. So the plot thickened when we went after some of these little red dots with MIRI imaging, which extends us out further into the infrared. So using relatively shallow MIRI data, we were able to put limits on the rest optical to near UV or near IR emission of individual little red dots. And here you can see a stack of the sample where you see that instead of the spectrum continuing to rise into the infrared, you see a characteristic turnover that suggests more stellar emission rather than red and black hole emission. But this is still very much an open question. There's still a lot of stuff that we need to do, and we're going to hear about this from Anna. So intermediate black holes in the early universe are not the only population of black holes that JWST is revealing that we were missing from our census. So from the days of Spitzer, we know that there are a lot of obscured AGN in the universe, but it's been really hard to figure out what fraction of obscured AGN there are, how many we've been missing. Spitzer could only find the most luminous examples. And so with the sensitivity and wavelength coverage of JWST MIRI, we can now find these AGN through small excesses in the AGN emission above the stellar emission. So that is demonstrated here. If you see there's a little bit of excess when you model this galaxy, and so the obscured AGN is revealed. And we're finding that MIRI identified AGN show up in both massive and dwarf galaxies, kind of in numbers similar to the amount of AGN that we knew about at cosmic noon before this. So we're really expanding our census how many AGN we can detect. And it's still early in terms of our understanding the connection between black holes and their host galaxies, but we're already finding that when we look at these MIRI obscured AGN and we look at their host galaxies seem to be more disturbed than their unobscured AGN counterparts detected in, say, the X-ray. This is kind of going back to that evolutionary pathway we discussed in the beginning, and might be a really big clue as to how these things are performing. So the last topic I want to touch on, which we go very fast, is why galaxies stop forming stars. So aging populations in quiescent galaxies are red and kind of fading, which has previously limited our studies to kind of the most massive examples, mostly at lower redshift. And also, aging kind of eventually erases the signatures of the quenching mechanism, making it kind of powerful for us to be able to extend our observations to more younger, higher redshift systems that were more recently quenched. And particularly with JWST, we can now identify the emergence of the first quenched galaxies, which kind of establishes how quickly the most massive galaxies in the universe can assemble. So prior to JWST, the abundance of quenched galaxies above redshift 3 was very unclear. We had orders of magnitude difference between different observational studies and also between theoretical predictions, so it's kind of all over the place. But now that we're having JWST results, so far in mostly small deep fields and a little bit wider, more shallow fields, we're already finding that number densities are on the high end of our previous studies, indicating that quenched galaxies are pretty abundant in the first 2 billion years of the universe. And we have kind of photometric candidates up to redshift 5 or so, which is probably not the highest redshift we'll find them. These are rare sources, so we need to extend to more area. On the bottom right here, you can see a near-spec spectrum of a confirmed quenched galaxy at redshift 4.6. So we have well-detected spectral features that really constrain the formation epoch and the star formation history of this galaxy. And in this particular case, it's indicating that this galaxy formed the bulk of its stars over about just 2 million years, or 200 million years, not quite as short as 2 million years. Okay, and then, so in addition to measuring these abundances, which is kind of the first step in understanding how galaxies are quenching in the early universe, JWST is also, again, particularly low-mass quenched galaxies in this case. So low-mass galaxies are thought to evolve differently than their high-mass galaxies. They're thought to be able to sustain star formation over long time scales. Some models put it at time scales longer than the age of the universe, but they're also maybe more susceptible to things like stellar feedback, gas stripping, interactions. They have shallower potential wells. They might be easily disrupted. So these investigations are just getting started, but we're already finding some interesting results with low-mass quenched galaxies. So on the left here, we see a very low-mass quenched galaxy observed at redshift 7. So it's very early in the universe. So with a massive quenched galaxy, it's already massive, so you know that it kind of has to stay quenched because it could only grow so much before it would be like the most massive galaxy in the universe, and that's kind of unrealistic. With these low-mass galaxies, they do have the potential to keep growing, and so the question of, how likely is it that this guy is quenched permanently? Could it rejuvenate? And so we kind of have this term now of mini-quenching, where we're trying to figure out if these quenching phases are not permanent and what kind of cadence they keep going on. Okay. And then one other thing, on the right here, we're seeing in a lower redshift of 3.7, we've identified a sample of low-mass quench galaxies in a relatively small Miri parallel for the JADE survey. To our surprise, multiple of these low-mass quench galaxies are associated with the cosmic rose, which Marcia showed on Tuesday. And the main components of this cosmic rose are actually a pair of massive galaxies. So there's the rose part itself, which is a massive dusty star-forming galaxy, and then its companion on the lower left is a massive quench galaxy, and then around it, circled, are a couple of low-mass quench galaxies. So this seems to be a whole group thing going on. And then when we zoomed out and we looked at the rest of the low-mass quench galaxies in our sample, we found that all but one of them was associated with a galaxy overdensity, even within our kind of small field. It's kind of hard to see, but outlined in purple. And so this is suggesting that, even at these early cosmic times, where it's interesting to even find low-mass quench galaxies, we need to consider the role of large-scale environment as maybe a primary quenching mechanism for galaxies of low mass. Okay. And so in conclusion, JWST is making huge strides in addressing these broad questions in galaxy evolution. We're really just getting started, so all the fun is still to come. And then I'm just going to leave you with this comparison at the top, which I guess is kind of hard to see on this small screen. But this is the spatial resolution jump from Spitzer to Miri for some of our favorite galaxies in our SMILES survey of good stuff. Thank you.